This is just a very quick proof using lattice planes of two things. Firstly, that the scattering vector S, which is defining our points in the reciprocal lattice, is perpendicular to the HKL plane from which the scattering occurs. And secondly, a proof of Bragg's law from this. So I've got a picture here of my HKL plane defined with my Miller indices with these intercepts here. And you can see, therefore, that I've got three edges to this plane. And these edges I could define mathematically as lines. And so this edge here would be defined mathematically by the line A over H minus B over K, this one by B over K minus C over L, and this one by A over H minus C over L. So that's the way of writing these lines in vector notation using those vectors. So what we could therefore say is what happens if we took the dot product of S with each of these lines. So S dotted with A over H minus B over K. So if I were to take this and dot it with this, I'd have this first term dotted with all of this. Now A star dot A would be equal to 1, and then I've got H over H, so that would just be equal to 1. A dotted with B star is equal to 0, and A dotted with C star equals 0, so those two terms would just be equal to 0. So from this first term here, I just get 1, and then I have minus B over K dotted with S, so if I do B over K dotted with this, again, the cross terms here would go to 0, and I just get KB star dotted with B over K. B star dotted with B would just be equal to 1, and K over K is going to be equal to 1, so this term would become 1. So this would just become equal to 1 minus 1, i.e. equal to 0. And I could do that for any of these three cases. So S dotted with any of these lines would be equal to 0. Now, if you have the dot product of two vectors together and it's equal to 0, remember the dot product of two vectors is equal to the modulus of those two vectors multiplied by the cosine of the angle between them. Now, assuming those vectors have some sort of length, that implies that the cosine of the angle between them must be equal to 0. And therefore, it implies that the two vectors must be perpendicular to each other. Now, that means that S must be perpendicular to this line, S must be perpendicular to this line, and S must be perpendicular to this line. Now, as all three of these lines together therefore define a plane, it must be the case that S must be the vector that is perpendicular to all of those planes. So what we're saying is that S is therefore perpendicular to that plane. So the scattering vector S is perpendicular to the plane of the HKL plane that it defines. Now, what does this then mean in terms of proving Bragg's law? Because I also said that I could prove Bragg's law with this. So let's think then, I've got this vector S that comes out in this direction, which I'm saying is perpendicular to this plane. Now, if I want to know the interplanar spacing of these planes, the interplanar spacing is just going to be the distance of O to this plane. Now, another way of saying that is I could just take the projection of any one of these intercepts onto the vector defined by these intercepts onto this vector S. And that should, onto the direction of this vector S in order to get the D spacing. So the direction of this vector S is just going to be given by S divided by mod S, shown here. Because that would give me a unit vector that's pointing in that direction of unit length. So I could take A over H and dot it with S over mod S, and that would give me this interplanar spacing from O to this plane here. Now, A dot S is therefore going to be A dotted with this, which would just be equal to H. And so this is equal to, this top expression here is just going to be equal to H. So I end up with H over H mod S, and the H's are going to cancel, which just gives me 1 over mod S. Now, this on its own is a really important thing for us to realise. that the d spacing is just 1 over the modulus of the reciprocal lattice vector that defines that lattice point. This is a really useful point, and why the reciprocal lattice is so useful. Because if we can define our reciprocal lattice and the distance on the reciprocal lattice, we can then just work out that distance and take the inverse, the modulus of it, and take the inverse, and that will give us our interplanar spacing here. So d is equal to 1 over mod s. But actually, we can go one step further with this. If we go back to our vector triangle that we drew from our diffraction from a general object, and if you haven't watched that video, you might need to go back and just convince yourself of this fact. What we have is we have a vector triangle that looks like this, where we've got S0, S here, and S here. When I drew it in the original video, I had S0 and lambda S and S here. Now I've just divided this through by lambda here, divided all these terms by lambda, but the same thing is true. And I've got this angle here, which is 2 theta, which is the scattering angle, which we said is the angle between the incident beam direction and the emitted beam direction. But actually, you can see here, I could divide this isosceles triangle into I could drop down a perpendicular bisector here and just have 2 right angle triangles. And within this right angle triangle, what I could say is sine of theta, which is just going to be that angle there, is going to be equal to the opposite, which is going to be half of this vector distance here, over the hypotenuse, which is going to be that distance there. So I could write sine theta is equal to mod s over 2 over mod s0 over lambda. Well, s0 is just a unit vector, so that's going to be equal to 1. So what I get when I rearrange this is I'm going to get mod s is equal to 2 sine theta over lambda. So if mod s is equal to 2 sine theta over lambda, I could therefore plug that into this expression here, and therefore get d is equal to lambda over 2 sine theta. Or rearranging it, I'd get Bragg's law, which is lambda equals 2d sine theta.